Now we will discuss the concept of the velocity of the approach as well as its relevance and importance for the measurement of the discharge over the weir. So first thing is that its definition. What exactly is the definition of velocity of approach, and what exactly its meaning, how the definition of this thing is going to affect the discharge over the weir or notch, and how the concept of the velocity of approach is implemented into the real engineering problems through some uh, empirical formulas which are available over there. So that in three sections we will discuss this part. So let's start with the definition. So the velocity of approach can be defined as the velocity with which the water approaches or reaches the weir or notch before it flows over it. So far, whatever the expressions of the discharge or weir we have derived, there we haven't discussed any point regarding the velocity of the water. So that you have to understand this particular point, that the equations we have derived so far has neglected the velocity of approach. So velocity of approach has been neglected. If any weir is available over there and if water is coming, definitely if water is coming, that means it, so some velocity it will definitely going to be over there. And during all the discussions we never thought of the inclusion of va for the any formulation of the q so far. So I'm writing the definition for the velocity of approach. So that is now now the second important thing is that how we will measure the velocity of approach. However, we can install any device that can measure the uh, uh, fluid velocity at that desired particular point. But however, the same thing is not feasible because water may be turbulent. So another indirect method for measuring the velocity of approach is the estimation of the q, that is your discharge, with the some changes we have to made in the formulation. So let's first of all need to understand why the velocity of approach is going to affect our discharge we are measuring so far. So let's the velocity of approach is va. So whenever the water is flowing over the crest and it is coming at a velocity of va, then definitely this presence of the velocity in the flowing water will create an additional head, and that head is equal to the velocity head. So velocity head so far we have discussed in the case of the Bernoulli's theorem. So it will be equal to va square by 2g. That is your velocity head will be created by the speed of the water. So the another aspect that for the evaluation of the expression of the discharge over any weir, what exactly we were measuring so far is that what is the head above the crest. So let's say the height of water above the weir is h. This h is when we are not considering any velocity of approach. However, once the velocity of approach is involved over there, this additional head should be also counted into the picture. So additional head is your velocity head. So this, if we include the head into this one, this profile should be somewhat like this one. This is your not actual flow line. However, this is the head at this location. So head at this location is coming all the way from this value. So at this particular point, if we talk about the what is the total head, so the total head, actual total head would be H plus HA, where your HA is VA square divided by 2G. So once we are considering this particular aspect, our formulation for the estimation of the discharge over a rectangular weir or trapezoidal weir, rectangular weir, trapezoidal weir, or anything else will be modified. So if we talk about what the expression we will use for a rectangular weir, so equation of discharge of or discharge over a rectangular weir when we are considering the velocity of approach. So velocity of approach is considered. Then Q will be 2 by 3 CD into L into under root 2 G, and then H is the head plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. That will be the equation of discharge over a weir once we are considering the velocity of approach into the picture. Now, another important thing. The next question is that how we will estimate the velocity of approach. So, estimation of the velocity of approach. So what exactly is there that whenever we will go to solve this problem, any kind of problem which is related with the rectangular weir, so we are not sure that what will be the Q. So however, in the any problem, we will be having the area of channel. So area of channel will be always known to us. So let's say the area of channel, that is your A. And similarly, length of weir will also be known to us. That will be known to us. And similarly, head over the weir, that will be also known to us because that we can measure. So and also the CD value will also be given to us. What we will do that we will estimate the Q value using the formula of we are having earlier without the consideration of VA. So that formula is this one that we have used so far. So in once you estimated this particular Q value, then what you will do that we will figure out that what is the velocity of approach by using this equation of Q over A. So this Q is what the value you got from using this particular equation. Now once you are having the velocity of approach, in the next phase you will figure out the additional head that is generated by the velocity of approach. So the head we will be finding out by using VA square by 2G. In the next problem, what will we do? Now we've got VA value as well as HA value. Now the same both things are available to us. So let's say this is our equation 1. This is your equation 1 and this is your equation 2. So in what we'll be doing now, in equation 1 expression of HA is involved into the equation 1. Now what we can do, we will be using the equation 1 now with the known value of HA so far. So we will be finding out the discharge using this particular formula, CD multiplied by L under root 2G in bracket H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. Now, using this particular thing, we will again get the Q value. So one Q value, you got this particular equation in first case. So what we can say, this is your iteration 1. The Q value you got from the iteration 1. And the Q value again you got from the iteration 2. So you will compare the Q value you got in the iteration 1 and the Q value you got into the iteration 2. Once the difference between the Q1 Q2 is very low, Q1 minus Q2 is very low, or they are just comparable or almost equal, then whatever the value of Q you are getting will be your actual discharge. Otherwise, you will continue to recalculate the value of Q. For example, the Q value you got into the iteration 1, let's say this is your Q2. So again you will divide this Q2 by A, you will get again a different VA value. Once you got the VA value, you again will find out what is the HA value corresponding to the VA value you got over there. Again, with this HA, you will use the in equation 1 in order to get the Q value. So let's say it's after the third iteration. This is your third iteration. And let's say this is Q3. You will again compare that whether Q3 is almost equal to Q2 or not. If it is almost comparable, then you can say the final answer is your Q3. So we will take a numerical problem on this particular aspect. This will be more easier for you to understand that how to approach for such kind of problems. Now we will solve a numerical problem on the velocity of approach. So the problem given to us is a rectangular weir of crest 0.5 meter is used for the estimation of discharge in a rectangular channel of 0.7 meter deep and 0.8 meter wide. So we need to determine the discharge. In channel if water level is 0.08 meter above the weir crest and CD value is 0.62, that is coefficient of discharge, and we have to take the consideration of the velocity of approach for the determination of discharge in the water channel. So let's start the solution part, which says that, so before starting any problem we should outline all the values given to us. Then it makes easier for us to understand the problem as well understand the approach how we should proceed the problem. So the length of weir is given to us. So length of weir is known as L. We have used this thing. So this value is 0.5 meter. Now the area of channel is also required. So area of flow you can say, or area of channel. So area of channel is your width into depth. The width is given to us, that is 0.8 into 0.7, that is 0.56 meter square. So that is the area of the channel through which the water is flowing. Now head over the weir is also given to us. So head over the weir is 0.08 meter. Now CD value is also given to us. So this value is 0.0. So let's start the first iteration. So in the first iteration, we will use our usual formula of the discharge, that is your Q is equal to 2 by 3 multiplied by CD into L into under root 2G h raised to the power 3 by 2. Why we are using this thing? Because velocity of approach is not known to us and right now we cannot figure it out. So if we'll just put all the values, this value is coming to be 62, L is 0.5 under root 2 multiplied by 9.81 and this value is 0.08 raised to the power 3 by 2. So this value is coming out to be 0.0207 meter cube per second. That is our Q value. So this is our first iteration. Now once we got this particular Q value, we will estimate the velocity of approach. So in order to just distinguish this thing, so our second iteration is we'll start, first of all we will figure out what is the VA. So VA is your Q divided by A. So in order to get the what will be the Q, this estimation has been done. Now we will put this value U207 divided by area, which is 0.7 into 0.8, 0.56, and this calculation gives us 0.3698 meter per second. That is the our velocity of approach. So this solution, this calculation gives us the 0.0207 divided by 0.56. That value is 0.03696 meter per second. That is the velocity of approach. Now using this VA, we can calculate the HA. That is the our head due to the VA. Head due to VA. That is VA is HA is equal to VA square over 2G, and that comes out to be 0.03696 square divided by 2 multiplied by 9.81. So this calculation gives us 6.964 10 to the power minus 5 meter, meter. That's it. Now using this HA value, we will be calculating the Q value for the second iteration. So Q value will be 2 by 3 CD multiplied by L under root 2G in bracket H plus VA, HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. And then if we'll put all the values, 2 by 3 CD 0.62, L is 0.5 multiplied by under root 2G, this is 9.81 multiplied by HA. H is given to us, that is 0.08 plus HA is 6.964 10 to the power minus 5, and overall is raised to the power 3 by 2 minus 6.964 10 to the power minus 5 raised to the power 3 by 2. That will be the final Q value. So we need to solve this equation. We need to put all the values and get what exactly its answer is coming out to be. So that is, so this value is coming out to be Q is equal to 0.02072 meter cube per second. So if you noted that Q value in the second iteration, this is the second iteration, and in the first iteration is almost same. However, we should always proceed for the one more iteration, so that we will be assured that whatever we are getting uh, is accurate. So third iteration. So in the third iteration, we will be first of all find out the VA value. So VA value will be corresponding to the Q value we just got over there, that is 0.02072 raised to the power divided by area, that is 0.56. So this is coming out to be nearly 0.037 meter per second. And then we will find out the HA value. So HA is VA square divided by 2G, so that is 0.037 square divided by 2 multiplied by 9.81. So this answer is coming out to be 0. Or we can say this is coming out to be 6.977 10 to the power minus 5 meter. So this value is very small. You can see HA value is almost close, 6.964. Now this is 6.977. So we will again find out the discharge using this Q value. So HA value, so Q is equal to 2 by 3 CD multiplied by L multiplied by under root 2G, and then H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. So we will quickly put all the values, that is 2 by 3, CD is 0.62, and then this is 0.5 under root 2, 9.81, and then in bracket this value is 0.08 plus HA value is 6.977 10 to the power minus 5 raised to the power 3 by 2 minus 6.977 10 to the power minus 5 raised to the power 3 by 2. And if we calculate this value is coming out to be 0.02037 meter cube per second. That is the Q value we are getting in the third iteration. So if we compare the third iteration value, Q value, this is also very close to the Q value in the second iteration. So now if we are getting the two close values, we can say the what the discharge we have got is the our final solution. Now there is one important point. However, for all the engineering problems, we usually take that 2 digits after the decimal points. So my advice to you is that for the all such calculation, you should use at least the 4 digits after the decimal point. For adopting this approach, you may get your answer in the third iteration always. Why exactly? Because in the first estimation, when you are calculating the Q value, this value is not involved into the VA. So this Q value will not be accurate. However, once you are going for the second iteration, this is your first, this is your second iteration. Now VA is over there. So definitely these two value will be different. Once you are using the iteration for the second time, again VA is involved, then most probably what exactly you will be seeing that Q2 and Q3 value will be almost same. Only when you are using 4 digits after the decimal points. If you are not using the 4 digits and if you are using the 2 digits only, sometimes your answer will be very much matching one. Then you have to think of this thing, and also Another point is that, so with this note of using the 4 digits after decimal point, you will quickly arrive to the exact solution in the third iteration. So I hope this particular lecture has made you more clear about the concept of the velocity of approach, as well as the how we should proceed for the such kind of problems.